All right, hello everyone. My name is Nico. I'm an assistant professor at UNC Chapel Hill, and been here for a couple of years. My lab works at the interface between optics, biology, and neurosciences, and computer sciences. And we're developing optical technologies that are specifically geared to help neuroscientists and help biologists in getting the data that they care about. So, in today's talk, what I would like to do, and since this is the first talk of this seminar, I would like to walk you all through a I would say hands-on approach to wave optics and holography, where we start from the very beginning. I always assume that people understand holography very well when joining a conference, but I could see how this is not necessarily like the topic of expertise of everyone here. So we can basically like start this and open today with what I would like to say is, the common core of what everyone should know to get into holography. So we'll do that, and then I'll talk to you about some of the algorithms that are out there to solve holograms, to compute holograms. And one of these algorithms that I developed when I was a postdoc, and then another one of these algorithms, which I'll show you how much better it is, has been developed by my grad student, Haas Ekbosh, who's here in the audience. I also say that Haas might be able to answer questions live in the chat. I also just joined the Slack channel, so by all means, post them wherever you wish, and I'll do my best to answer them on the fly. And if you want to interrupt, that's okay too. We're not such a big audience that it's not feasible. So in this talk today, we're going to do a couple of things. There's a couple of Matlab demos that I've generated. You can access them via the code or open source tab on my website. And also the DeepCGH code that we're going to be discussing is available on GitHub. We also wrote a Google Colab notebook that we're going to walk through together that allows you to test it on their Google remote servers, which basically give you a good ground to start with. It's something that we've tested and it should run no matter what computer you use. And that way you can get started from something that works and then, edit it to whatever your needs are. So to get started, I'd like to just give you the only, simplest possible introduction to wave optics. So the only really easy wave that we know how to simulate is the point source. So if you have a space that represents the volume that we live in, light is a deformation of the electromagnetic field that satisfies the wave propagation equation. And so if you have a point source with an oscillation, it's a sinusoidal oscillation, the electromagnetic field looks a little bit like this. And you can represent the oscillation of the electromagnetic field, typically the electric field, using its amplitude and its angular frequency. In optics, we don't really like to use cosine functions. So typically we use the real part of a complex function. So our reference to the complex field, this quantity right here. And very often we don't even write that we're talking about the real part. We just write the complex field here. The amplitude is typically proportional to the electric field. And the intensity would be the square of the amplitude distribution. The point source is really interesting because we can solve the field in the rest of the volume very easily. If you are anywhere else in the field, at a certain distance r, for instance, you can calculate the time it takes for the wave to go from the source to the other point, and you basically can write the state of the oscillation at another location in space using a phase delay, e to the I kr, which is this quantity right here, where k is the wave number or the spatial angular frequency of your field. The wave may be attenuated over space. We're just going to ignore that for now. You don't have to worry about that very much until you start doing really fancy optics. Now, the reason why we study point sources and we like them so much is because the wave propagation equation is a linear differential equation, which means that if you have multiple point sources, all you have to do is compute the solution for each of them and then add them up. The best example is the two-slit aperture example, where you have a wave coming in from the left side that is modulated by two apertures that are small enough to be counting as point sources. So if you want to calculate the state of the field anywhere in space, for instance in B, all you have to do is add the contribution of the first point source here, this oscillation, modulated by its delay along the path R, plus the wave coming from the second source, modulated by the delay along the path R prime. If you do a little bit of math, you can simplify this expression, and you can find that the state and the amplitude of the oscillation really has to do with the difference between R and dr. If the difference between R and dr and R prime is a multiple of the wavelengths, then the waves interfere constructively and you have plenty of light. And if it's a half wavelength, they interfere destructively and you see these areas where there is no light. So that's the example with 1-point source, 2-point source. And more generally, you can treat any wave as a superposition of point sources. That is called the Huygens-Fresnel principle. It's the natural expansion of this principle of superposition to a more general wave. So if you have a volume of space right here, a contour, you pick the contour carefully to have as much leeway on determining the field. And imagine, for instance, you have a wave coming in and you can determine at the boundary a window, an input window, where you can express the status of the wave with locally the amplitude and locally the phase function. Well, if you want to calculate the field inside this contour, all you have to do is treat each point right here as a point source and match the amplitude and the phase of each point source to the incoming wave that you would like to simulate. And then if you want to calculate the state of the field, let's say at this location right here, all you have to do is add the contributions of all these point sources, including their respective phase delay. And if you sum that up, you'll be able to integrate those contributions and calculate the complex field anywhere within the contour. So in optics, wave typically propagates along what is called the optical axis under a paraxial approximation. So this Huygens-Fresnel, which is a general physical principle, can be simplified into an expression called the Fresnel wave propagation equation, where let's say you have a field, a complex field here, determined by the cross-section along the plane in z equals 0. The complex field that is right here can be expressed in form of like its complex amplitude and phase. And if you want to calculate the state of the field anywhere in the remainder of the volume, you can use this equation that basically tells you that the 2D phase and amplitude that you have defined in this plane right here as a 2D array of point sources, for instance, will entirely determine the state of the oscillation, the complex field, and the rest of the two-dimensional volumes, simply by adding the contribution of all the points right here, treating them as a point source with their respective phase delay by calculating the path between a point of origin x prime, y prime, and a target point at coordinate x, y, z. So in the code that I've shared, and I'll share my screen to show you, we have implemented this operation. It's a convolution product. We have implemented this operation so you can sample a complex field in 2 dimensions. If you specify the wavelengths, the pixel size, what physical space it represents, and the propagation distance, you can use Matlab, and in a couple of FFTs, you can calculate the state of the field at a certain distance. So we give you an example right here. If I take, for instance, the UNC logo as my amplitude function, I assign to it a phase that is equal to 0 everywhere, just for simplicity. Using the complex field made of this amplitude and this phase for a certain dummy wavelength, pixel size, and propagation distance, I can calculate the state of the amplitude at a certain distance. And you can see here the effects of wave propagation, the characteristic patterns that you observe right here. If you change the phase of the field, it will affect the amplitude. So here we have another example. We take the same amplitude at z equals 0. We assign a randomized phase to it. And if you propagate that new complex field to the same location, you'll see that it significantly affects the status and the amplitude of the wave. The amplitude that you visualize here is nothing but the square root of the intensity you would see if you were to put a physical screen at this location. So you can run this on Matlab. So I'm going to share my screen here. So in the code that you can download, we have encoded the propagation function here, right here. It's specified here in the form of like a convolution product, which is basically done in the Fourier domain. And if you run the demo here, right there, you can specify the physical properties of your space. And we have this little demo here where we go sequentially depth after depth, and you propagate the field between 0 and 10 centimeter, and you can see the amplitude at a certain distance. So this is just to give you the tool to simulate the propagation of waves. Nothing really interesting to add on that, so I'm just going to move on. Settings. There you go. So you typically don't propagate light typically just through free space. The second most common element you'll find in an optical path is a lens. And to simulate the propagation of a wave through a lens, we typically simulate not just propagation through the lens, but propagation through what is an FF system. So a portion of space of size F, a length, a focal length F, and another portion of space of size F. Here we define the input complex field as the two-dimensional complex field here called A of X, and the output as the two-dimensional complex field B of X prime at a distance F from each other side of the lens. In this particular configuration, if you ray trace a bunch of rays that land in X prime, you can calculate the field in X prime by applying the same Huygens-Fresnel principle. You can say that the field in X prime is the sum of the contribution of the field in A integrated over X. So here we do the one-dimensional integration, but it naturally expands to the two-dimension, modulated by the difference of path going from the origin right here to X prime. And the path that it takes to go from the origin to X prime depends on where you're located along this axis. If you define this to be the reference path, the path for a source at location X will take an extra amount of time, and that extra amount of time it takes for it to travel corresponds to this extra traveling distance dr here. And you can express dr using basic trigonometry to the first order as proportionally linear to F and X prime. So if you write that and simplify this expression, you write an expression that gives you that B of X prime is this quantity right here. This is nothing else than the Fourier transform. So the definition for the Fourier transform of distribution A would be multiplying A by e to the minus I2p kx. And if you map the k quantity to the properties you have right here, and you will find that basically the field you see in B is nothing but the Fourier transform of the field in A with a scaling factor where the k coefficient here, the spatial frequency coefficient here, would be X prime over F lambda. So in short, if you take an optical system made of a single lens in the FF configuration, it will operate a Fourier transform on your complex field. So we have also implemented that. We did so just to simplify the operation. So instead of just calculating the Fourier transform, we also calculate the new pixel size in X and Y to give you a realistic rendering of what you would see through a lens. So you can take an input field, field 1, specify its pixel size in X and Y domain. So that gives you basically this realistic description of what the physical space size represents. And if you use this operator, using this, specifying the focal length and the wavelength, it will output a complex field, which you visualize right here, but also the PSX and PSY that represents the pixel size in this secondary complex field right here. And so now that you go back to your optics book, you say, well, what happened if I put two lenses? I basically create an imaging system, and that's basically telling you that a Fourier transform operated twice is the identity function. So here we have a little variation on that. Instead of doing two Fourier transforms in a row and retrieving the same image but flipped, we, in the Fourier domain, add a pinhole aperture, radius A, that cuts off all the information beyond a certain radius A. And what that represents, basically, is that you cut off the high spatial frequency in the Fourier domain, or in an optical system, you create an aperture-limited imaging system where high spatial frequency don't get to propagate. And by doing the simulation here, by Fourier transforming Mr. Fourier twice and using a spatial filter in the Fourier domain, you see something that you're very familiar with in microscopy, which is that your resolution, the resolution of the optical system, is now limited by the aperture and the size of the smallest spatial frequencies that are allowed to transit through the optical system. So we have, again, created a simulation that allows you to run those particular to visualize those particular elements. So we upload an image, we specify a complex field based on that image, where the amplitude is the square root of the complex field. And then what we do is we propagate through a first lens here. We limit the aperture of the optical system by erasing or zeroing everything else in the complex field except within the size of the aperture. And we propagate again. And if you run this simulation again, you'll basically observe the simulation that we're talking about. This is the intensity after a first lens. This is what happens when you crop it. And this is the intensity you get after the second lens. So these are tools that allow you to quickly and rather simply simulate the propagation of optical waves through an optical system. I like to say that this is kind of a practical tool because with very simple modification to the code, you can actually simulate the point spread function of a simple microscope. All you have to do is create an optical system made of two 2F system. One represents the objective with a short focal length. The aperture limitation represents the diameter of the back aperture of your microscope objective. And then here another F system represents the tube length of your microscope. And if you place an infinitely small point source in the input field, you can look using the simulation at the output field in the three-dimensional domain, and you can calculate a representation of the point spread function of a microscope. So basically the characteristic distribution that will visually show you how the microscope is able to image an infinitely small source. And you can tune the parameters of your optical microscope and see how tuning those parameters will affect the resolution of your microscope. So with that, the introduction is over, because with that you have a complete toolbox. If you need to simulate the wave propagation, the propagation of a wave through any combination of spherical lenses and free space, you can do so using a combination of the functions we've discussed. If you want to go through a first lens, you do a FF transfer. That will bring your complex field from here to here. If you want to go through another lens that is not placed conveniently, you can back propagate your complex field to a more appropriate location, and then using another FF system, calculate the output field right here. So by alternating between propagation and FF system Fourier transforms, you can simulate the propagation of a complex field through any custom optical system made of ideal thin lenses, and basically get an idea of how every single optical system operates. I'd like to say that the propagation and the lens operation FF are both reversible operations, so you can simulate the propagation of the field backwards and forward through those optical systems. So moving on from that, that's all I had to say about this first step. Is there any questions I can answer at this point? So I want to make sure I'm not like leaving anyone out. Any questions so far before we move on? All right. So moving on, the type of problems we're interested in are holography, holographic hologram computation. And those fall within a broader category of problems that are basically like non-obvious problems in wave propagation. With the wave propagation equation, we've been able to show that once you know the phase and the amplitude of a complex field anywhere in space, we can deterministically calculate the state of the wave in the rest of the three-dimensional domain. But in holography, we're dealing with a category of problems that is slightly different, where the information is only available partially or in distributed fashion. Like some of the information available in one portion of space, some of the information is available somewhere. So typically, when we want to create a hologram, on the side of the object, we know the intensity, we know where we want to put the light, but we don't know anything about the phase. And on the side of the modulator, the SLM that we use to generate those holograms, we typically would like to calculate the phase that must be applied right here. And we happen to know what intensity is available because we know what the laser looks like. So this type of problems where the information is constrained at various locations is typically ill-posed and must be solved using more advanced form of algorithm, not just by simulating the field. So I'm going to skip that slide. It's a horrible slide. I should not have put it in there. But phase retrieval and holography are analogous problems that are, have a lot in common, but basically fall within that same category. So in this talk, we're going to specifically talk about computer-generated holography. So in computer-generated holography, we start with a laser beam, which gives you a nice, coherent, clean oscillation. And that wave propagates forward in an expanded fashion and will typically be modulating using a spatial line modulator. So a spatial line modulator is a two-dimensional chip made of pixels. Those pixels are little liquid crystals, typically. They can be tuned and actuated using a voltage. And depending on how much voltage you apply on each of these crystals, you will introduce a phase delay that will slow down your wave proportionally to the value that you put in. And after transmission or reflection at the surface of the SLM, you end up with a modulated wave that is modulated in a custom fashion as specified by the instructions you give to the SLM. That modulated wave propagates, so that's what an SLM does. If you apply a voltage, it shifts the liquid crystal, changes the optical properties. And after this wave, modulated wave propagates through an optical system, you end up with a distribution of light in the image plane or around the image plane if you're trying to create a three-dimensional pattern. Now, in computer-generated holography, the goal is knowing what pattern you want in the image plane, calculate the best possible wave modulation you can apply on the SLM that will render this illumination pattern. And this is typically an ill-posed problem. Why? Because typically you try to generate an illumination pattern in 3 dimensions, so you specify a lot of constraints. And your ability to modulate the wave is A, limited to phase only, and B, restricted to a 2-dimensional plane. So when you're trying to make 3-dimensional holograms and you specify illumination pattern in 3D, well, in most cases, you don't even ask for something that's possible, especially if you're a biologist. You typically want your light in targets, in neurons, in cells, and you specifically would like to avoid light anywhere else. Well, that typically violates the wave propagation equation because it violates conservation of energy. If you want to shoot photons at a specific target in 3D, your light has to come from somewhere else. So you cannot have a situation where there is light in this isolated cell in XYZ and no light around it. So that typically is not feasible. But because we understand what the goal is in biology, you can specify this illumination profile and let the algorithm find how to best match it, knowing that you will not be able to get an exact solution. But more generally, you specify your illumination in 3 dimensions, so that's a lot of degrees of freedom, but your ability to modulate the wave is restricted to a 2-dimensional modulation. So typically, the solution of computer-generated holography is typically an approximate solution. Your algorithm's goal will be to best match the illumination you want, knowing that an exact solution is rarely possible. So the simplest algorithm that is out there to compute holograms is the Gershwin-Saxon algorithm and is based on these operations of propagation through an optical system that we've calculated before. How do we do that? Well, we have our optical system. We start from the size on the side of the modulated SLM. So sorry, this should be an SLM right here. Here at the SLM plane, the amplitude is set. It's defined by how you illuminate your SLM. It's typically a nice and clean Gaussian beam if you have a clean beam line. So you happen to know what the amplitude is. The phase is the output of your algorithm, but we don't know it yet. So we're going to start by assigning to our beam a random value. We know this is not the right thing to do, but once we have the phase and the amplitude, we can start doing calculations. So we assign to it a random value. We initialize the algorithm with a random phase. Now we have amplitude and phase. We have a complex field. So we can use our operations to simulate the propagation of this wave through the optical system. And we will go to the object field, where here I have a camera, but basically this is the plane where I'm trying to make a hologram. And you have an estimation of the complex field at the image plane. Here, because you started with something random, the odds are that at the first step, you're going to get some, let's say a more polite word for garbage, but basically something that doesn't look anywhere near what you want. The idea of the Gershwin-Saxon algorithm is to enforce constraints at every step. So here at the object plane, because I know what illumination pattern I want, I might as well enforce it. So what I do is I take my complex field. I'm going to keep the phase because I don't want to touch it. I don't have a reason to touch it. But I'm going to update the amplitude of this complex field with a more realistic amplitude. I'm going to match the amplitude to the amplitude of the, not the observed data, but the amplitude of the illumination pattern that I'm trying to recreate. Once I have this updated complex field, I can use the very same tools to propagate backwards towards the SLM, the spatial light modulator. And in this plane, I will have a new complex amplitude and a new complex phase. The complex phase I'm getting here, sorry, the new complex field with an amplitude and a phase. The phase I'm getting here is perhaps a slightly better estimation of what I should, in the end, put on my SLM. The amplitude, however, because of the previous steps, is no longer looking like the amplitude of the laser beam. So at this step, what I'm going to do is I'm going to keep the phase and, again, update the amplitude to match what the laser profile is. And I'm back to square one with, that time, a new phase that is slightly better and a new complex field that is matched to what my laser is able to provide. And I can do this operation over and over. And the beauty of the Gershwin-Saxon algorithm is that without much proof, it will happen to converge towards a often suitable solution to the wave propagation equation. After a few loops, the updating of the amplitude is no longer significant, and the updating of the illumination pattern right here is no longer significant. The algorithm stabilizes to a solution where we have an accurate guess of what the complex field should be. So we have coded that as well. If you download the code and run this demo here, we have a similar process. So I'm going to skip the steps that are meant for display and show you the core steps. First, we initialize our beam with the amplitude that we want. And here, not a random phase, but we just set the phase to 0. You can do whatever you want. That's the initial complex field. And then in end cycles, we're going to propagate the field to the image plane, propagate the field first backwards to the SLM, update the complex field by matching the amplitude to the laser amplitude profile, propagate forward to the image plane, and again here, amplitude, update the amplitude to what we want it to be, our target amplitude. So exactly as I said in the slide. If you run this operation over and over, we can visualize it at every step of the way. You can see the first step is pretty ugly, but very quickly, the image that we get seems to stabilize. And you can find, the phase on the SLM. And you can see that here, for instance, we're not able to get a perfect match. That's a common problem in holography. But we're able to get an illumination pattern that resembles what we're trying to do. So you can, play with this algorithm as much as you want. It's meant to be edited, but it's also written in a way that is perhaps as easy to display as possible. So this is the simplest possible algorithm out there. The beauty of it is that it's really easy to implement. It's 4 lines of code, really. If you ignore all the fancy display that we're coding that takes forever to code with Matlab. But it's perhaps the easiest one that is out there for its simplicity. The downside of it is that it's not an algorithm that is known to converge very reliably. It's known to converge, but it's not known to find. It's specifically known not to converge to the optimal solution. In fact, we don't have, even as of today, an algorithm that can reliably identify the optimal solution of the CGH problem. It's still an open-ended question. The solution is also known to not be optimal, and that's because we were able to come up with better algorithms. So I'm going to show you one of these algorithms based on direct optimization. So this is something I developed when I was a postdoc. The idea is that you can phrase the computer-generated holography problem as an optimization problem. If I take a laser beam and an SLM, by applying a phase on my SLM, the amplitude and the phase give me a complex field, and deterministically will give me a 3-dimensional illumination profile out of XYZ. So you can see a holographic setup as an operator that takes as input a phase and gives you as output an illumination pattern. Now, if you specify an illumination pattern target, you can specify a volumetric illumination target. You can write the holography as an optimization. You can measure the difference between the hologram that you get and the hologram that you want using the cost function, basically like the L2 norm, for instance. And you can say that, well, the hologram that you want is the hologram that minimizes the error between the illumination pattern that you want and the illumination pattern that you will get when applying the phase phi on the SLM. So that optimization problem, formulated as such, is non-convex, is multidimensional. There is as many variables as pixels, and is therefore extremely difficult to solve. What we did in this publication in 2017 is we decided to use brute force and use gradient descent on a problem that was non-convex. And what happens when you do a gradient descent on a non-convex problem? Your algorithm will identify a minimum. It might be a local minimum and is unlikely to be the global minimum. What we found is that by using gradient descent optimization on this type of problem, we were able reliably to identify better solution than the Gershwin-Saxon algorithm. And if you think about it, that's because the gradient descent, even if it's imperfect in this type of problem, actually performs a lot more explorative capabilities than the Gershwin-Saxon algorithm that basically follows just one path. This gradient descent optimization explores simultaneously many more paths, and therefore is likely to find and fall into a better solution. So we kind of compare those algorithms by measuring the time it takes to compute the hologram, and using a cost function like the L2 norm, we measure the accuracy of the hologram as a function of the number of steps. And so here we display, for instance, the Gershwin-Saxon algorithm, and you can see that as the number of steps increases, the algorithm has better accuracy. Of course, stabilizes to an accuracy level that is not 1. And with this algorithm, we're able to find that if you are willing to spend even more time and explore more holograms, you would be able to get slightly better, or actually significantly better, holograms. So that envelope right here represents the area of feasible holograms, the one that we can calculate experimentally. But if you look at that diagram, it's still not very satisfactory. And specifically, it's not satisfactory for the type of problems that our community right here today is interested in solving. We're interested in using holograms for the purpose of stimulating neurons or for observing neurons for optogenetics, for calcium imaging. And so if you look at this video that we recorded some data, the type of data we see, like those calcium patterns that we see here, indicative of like the type of activity you see in an awake brain, they happen quite fast. An action potential is on the order of a millisecond. The biological processes that we're interested in tracking, they can go at speeds up to 50, 60, I would say 100 hertz just to be on the safe side of things. So speed is of the essence. So if you compute a hologram and it takes you 10 seconds to compute it, it's like having a conversation and taking 10 hours to respond. By the time you're ready to send your answer, the person you were talking to is likely to be thinking about something else, and the message is not going to be conveyed properly. And so speed is of the essence in the application that we're interested in, because we want to be able to send a hologram in direct response to an observed pattern, and we don't have the information about what to send until we visualize the activity. So if you want to have a two-way communication with the brain at the pace of the awake brain, you need speed. You also need accurate hologram. So an accurate hologram places the light where you need it to go. An inaccurate hologram wastes photons. And since we're doing multiphoton microscopy, having photons placed at the right location is very relevant. So this is just a small reminder. In regular fluorescence systems, you send blue light and you get green light coming out of it. This is what happened in this fluorescein cuvette here. And that process is linear. It's rather efficient. It works at low light. It's beautiful. The downside of it is because of conservation of energy, light has to travel all the way to your target and excites everything above and below. That image is the reason why so much energy has been invested in developing multiphoton systems. With multiphoton systems, you, instead of exciting with high energy photons, you cut the energy in half. You excite with infrared photons, but you pack your photons in space and in time using femtosecond lasers, so that you create the conditions where two photons can be absorbed at once. That process is actually very, very unlikely to happen. That's why you pay good money to get those femtosecond lasers. And you group the photons not only in time, but in space on the target. So if you're going to do holography with a multiphoton process, it's in your interest to have the best possible holograms, because an inaccurate hologram will send the light in random locations. You remember the UNC logo with the Gershwin Saxon? The fact that we have poor contrast means that the photons that we try to send towards the logo are bathing in a sea of randomly distributed photons. If you have randomly distributed photons with a multiphoton process, those photons will propagate nicely around the targets that you're trying to get. They will not at all contribute to the two-photon excitation process that you're so dearly trying to get. But more importantly, they're going to be absorbed eventually by your brain tissue in the form of heat. Keep in mind, the multiphoton excitation process is highly unlikely to happen. Statistics is in the score of the intensity. But more importantly, if you want to excite one neuron, you need tens of milliwatts of light per neuron you're trying to target. So in the end, you have a lot of heat being deposited in the brain. In fact, in those algorithms that we've been developing, in those technology that we've been developing, the number of photons that we're able to shoot at the brain and the number of holograms that we're able to generate simultaneously have been limited not by our holography capabilities, but by the amount of light that we are allowed to send in the brain before cooking the brain. And so if you are able to come up with better holograms, you'll be able to target more neurons without having to increase the laser power. And so you'll be able to target more neurons in parallel and do more neuroscience brain modulation experimentation. So how do we go about that? Well, we looked at our algorithms and we say, well, if we want to go faster, one of the things that needs to be done is get rid of the iterations. We need a non-iterative process. But the holography problems remains a nonlinear problem. So when you start throwing those words around, a nonlinear operation, a nonlinear calculation without iterations, you end up with the deep learning world. Deep learning is a great candidate to solve that type of problem. So we came up with an algorithm that computes holograms using the tools of deep learning to do so. So our input is the target intensity that we want, target amplitude distribution. Here it's in 2D, but you can actually specify in 3D. And we developed an algorithm that uses a CNN to output the complex field or to infer a suitable complex field at the image plane. The reason we did that is that CNNs, they operate using convolutions, and they're specifically good at performing nonlinear operations when the input and the output look similar. Like CNNs are great for colorizing old movies. The input is a black and white image. The output is a colorized image. Those images share spatial features. So if we were to use a CNN to directly compute holograms, for instance, by directly outputting the phase at the SLM, that's one option. That's one way to go. But because the phase is defined in the Fourier domain, there is actually no physical and spatial features shared between the input and the output. So that strategy has been actually tried, but is actually quite inefficient. But since the phase at the SLM and the complex field in the image plane are deterministically linked to each other, it doesn't matter what we output. We might as well pick something that shares spatial features. So that was kind of the key to our work, is to come up with a CNN usage that best leverages the CNN computational capabilities to solve optical and computational problems in optics. So our CNN, what it does is it takes as input one image in the image plane, or a series of images around the z = 0, the image domain, and it outputs what is a most likely complex field representing the three-dimensional distribution that we want. Once we have a complex field in the image plane, all we have to do is do a single reverse propagation back to the SLM and keep the phase, and we basically end up with the solution we want. So during operation, that's all our algorithm needs to do, and it outputs the phase without iteration. The only thing that we need to do to make this work is train the CNN. The CNN has a wide array of space parameters that needs to be adjusted so that the CNN gets to perform the operation that we want, and that has to be done by training. So unfortunately, training a CNN to perform holographic tasks is not really something that we can do, because there is no algorithm that is able to spit out ground truth. We could train it using other algorithm, but then outperforming previous algorithm might be difficult. So what we did instead is we implemented, and this is really the beauty of the work of Haas, we implemented unsupervised learning technique. What we did is we start with randomly initialized parameters, and we take the phase at the SLM that is outputted there, and then we use our forward simulation tool using the amplitude provided by the laser, and we get an estimation of what the output will look like when we recreate it in the image plane. And so by comparing the amplitude that we get to the amplitude that we want using a loss function, we can very quickly in simulation evaluate whether or not our CNN is doing the right thing or not. And because all those steps here are differentiable with respect to the parameters of the CNN, we can actually use that results to guide the updating process of the CNN parameters. So we generate basically a large population of test sample, and using this loop operation in a training step, we come up with an optimization technique that updates the space parameters of the CNN and trains the CNN unsupervised. And because we don't specify ground truths, our algorithm will update the CNN parameters as long as these updates are improving the outcome that we're seeking. And so we are basically enabling the algorithm to outperform previous techniques. So there are a couple advantages to this thing. The first thing I'd like to point out is that the model parameters, the CNN shape, can be tuned. So you can pick a very large CNN if you want this operation to be done really well. This will limit the time, the computation time. You can actually reduce the size of the CNN using interleaving techniques. So you can actually tune the CNN size to have the computation time be fixed to whatever tolerable computation time you want. You can update the loss function to train the CNN for a specific type of optimization. Maybe you care more about uniformity in your targets. Maybe you care more about brightness. This can be coded in the loss function. And if you code it in the loss function, it will be coded into the training. So you will further refine the training of your CNN algorithm to the specific task you're trying to optimize for. And you can pick a set of training data set that are application specific. If you're trying to make blobs, trying to make squares or images of cats, you basically can select a population of training images that is representative of what you're going to eventually feed your algorithm. So we did that, and this is the results. So here are Gershwin, Saxon, and Deep CGA and Novo CGH algorithms represented as a function of the computation time, and accuracy is a function of computation time. The previous results stand. We have two examples. We have a three-dimensional model with 512 by 512 by 7 depth planes, and a bigger one by 1024 by 1024 and 11 depth planes. And what you can see is that, notoriously when you increase the model size and generate larger holograms, things go slower. But consistently, what you find is that in comparison to their iterative counterparts, the technique that we developed is not only significantly faster, and we're talking order of magnitude on the log scale here, but also happens to be more accurate. That is, we were able to come up with holograms that the previous work that had been done on the topic were not able to achieve. So we're able to come up with better solutions. When we developed Novo CGH, our argument was like, look, we found better holograms. Our optimization method is falling into local minima of cost, and we understand that those local minima seem to be consistently above Gershwin-Saxon. And what we said in many presentations, wrongly say, well, what we think is happening is that of all the local minima that our algorithm may land in, they all happen to be located about at the same level, and that perhaps, this is as good as it's going to get. With this result, we basically found that it's possible to compute holograms with slightly significant better accuracy. So the idea is that that previous method was still kind of far from optimal holography. And the same logic stands today. This is our algorithms. It's the best algorithm we can find so far. Nothing tells us that better algorithm cannot be created that will continue to outperform the results that we're getting right here. So before we move on to show you the results that we have on multiphoton excitation, I'd like to walk you through a test of this deep CGH algorithm. And actually, so you can basically look that up on our GitHub. So this is the GitHub for the lab. This is our deep CGH. Actually, the simulation are here in the intro to holography. The Novo CGH code is available right here as well. This is an upcoming paper in a couple of weeks. And deep CGH is right here. So Haas has curated this beautifully with diagrams and instructions. So basically, you can download it and run it on your computer. But also because of the mnemonic conference, actually, this was something that the team of Andrea's lab had developed for Kaiman. We actually used a Google Colab notebook to do a simple demo of deep CGH. So Haas, if you want to unmute, and you're welcome to chime in, because like you wrote that and I only went through a couple times, but you're welcome to walk people through the steps. If I say anything wrong, please don't hesitate to chime in. So this is a step-by-step operation. The first thing this notebook does is it clones deep CGH from the GitHub. So you basically upload the latest version right here. Then we have a step in which we import the deep CGH modules from our code. Here in this next step, we specify the properties of the training data set. So the idea is that you can adjust the shape of your holograms to different form factors. You can update pretty much every parameters that is relevant to the optimization, the number of samples, the type of intensity distribution we're going to look at. There's a lot of variability in those patterns. We give you one example of training data set. Anybody can do that. We generate a data set. So here, I think the data set that we generate is 100 sample holograms. Is that correct, Haas? Or am I looking at the wrong?
This is just meant to show. This is just an example.
Yeah. So here we generate a
more number of samples is better.
Yeah, we generate a training data set just for the purpose of this demo. Then we specify model parameters right here. And then we create a deep CGH module and train it. So in the GitHub account, we already trained that specific model for a bunch of epoch. I think something like 100 epochs. Each epoch takes time to train. So the training part is extremely time consuming, specifically if you use large models. The beauty of it is in the operation. Like once you're trained, things can go fast. But we also have saved trained models that see the algorithm spits out that the model already exists. And so here what we're doing, just for the purpose of displaying, is that we're going to add one more epoch of training to our algorithm. So this is just to demonstrate that things work. Here we're only going to do an additional epoch. So we start from the trained model that we have uploaded from GitHub, and we're just going to run the training step for the purpose of demonstrating that it works one more time. And this step should take about 10 seconds, if I recall. Time for a sip of coffee. All right, I think that's it. So once the model is trained, sorry, go ahead, Haas.
Yeah, it was done. I was just saying.
So once the model is trained, we generate a random sample. So we pick one of the images, and this is the input is our image data. The output of the DCGH hologram is the phase. So we can run this and time the operation, and then we can use the phase that we calculated to propagate a simulation of the hologram, create a reconstruction, and display the results. So this thing will output a frame. So here, this is our three-dimensional hologram, a bunch of blobs with variable intensity. That's the input. That's the SLM phase that is inferred in 11 milliseconds. And if you propagate this phase with the laser amplitude that's provided, this is the hologram that you reconstruct with the algorithm. Now, just for the fun of it, we compare deep CGH to Gershwin Saxon. So we picked 100 steps. Maybe this is a little bit pushing it, but basically, to give you a comparison, 100 steps is not as greedy in space because it's step-by-step operation, but greedy in time, which is one of the main drawbacks we had there. And similarly, we calculate the time. Similarly, we run the reconstruction step on the very same data set, and you'll be able to visualize the results. So first off, it takes 22 seconds to compute, so significantly longer. The SLM phase is slightly different. Yeah, I can actually see some variation. I don't know exactly what happens there, but basically what you see here mostly is that in the reconstructed steps, the hologram, especially in 3 dimensions, Gershwin is kind of like difficult to calibrate, but the reconstructed image is still not there. Like you have a match of your holograms, the images match what you're trying to get, but the SLM phase is still like not fully optimized. And in that particular 3D case, it would benefit us to run it for a couple more operations. But basically, this is the same summary image to show you that like we're basically able to get significantly better and significantly faster computation. So you can, copy, paste, and edit this thing to test your code. You can download the code on GitHub and set it up on your expensive microscopes and try to see if you can get better photo stimulation. What I want to show you is a few slides that will convince you to upgrade to that particular model. So sorry about that. The type of device that we have implemented our system on is a multiphoton microscope. So right now it's configured as a standard multiphoton microscope. Laser beam goes onto the SLM, and we're trying to create a 3-dimensional excitation profile that targets multiple neurons at once. And for the purpose of visualizing what we're doing and calibrating, instead of shooting at neurons, we shoot at a thin 2D slice of fluorescent material, and we scan this apparatus in Z to visualize plane by plane how the 2-photon excitation happens in 3 dimensions. So what we did is we computed the same 3-dimensional hologram using the 3 types of algorithm that we've been discussing: Gershwin, Saxon, the easy one, Novo CGH for direct optimization, and Deep CGH. We've done that for a bunch of holograms. We've gotten simulation and experimental results. In this first experiment, we compute the amount of laser power that's coming out of the objective. So that's basically a measure of how much your brain is going to be heating up. And we see that with the 3 algorithms, the amount of output laser power is pretty much the same. Small variability observed, but not very significant. You basically get the same amount of light on the objective, so the same amount of heat. But if we scan in 3D and look at the total brightness or the piecewise brightness in every spot in the target that we're trying to represent, we found that as you go through better, more accurate holograms, there is a lot more 2-photon excitation and 2-photon fluorescence happening in the targets that you're trying to observe. So we divided one data by the other, and that basically shows you the 2P gain and the benefits of the 2-photon technology. And that's basically what you get for upgrading to the software, is that you compute better holograms, they're more accurate. So for the same amount of laser power and the same amount of heat going into your brain tissue, you get, on the order of 30% more illumination capability and excitation capability. Combine that with all the progress that is currently being made in developing responsive opsins and responsive reporters. The idea is that this is the kind of technology that will allow you to target more neurons in parallel. So this is some of our experimental results. We scanned the slide.
Can I ask a quick question, Nico?
Go ahead, Darcy.
Here, I'll turn my camera on. So some of the things that you've been showing are spots, and that's something I know a lot of people sometimes wonder about: spots versus shapes versus whatever. And if I remember the kind of some previous presentations, your algorithm works well for the kind of the full class of things you want to generate. Is that correct?
Yeah. So it turns out there is some cross-compatibility. You can train on spots. So these are not diffraction-limited spots. These are actually disks, because we didn't implement the 3D shot technique yet. We actually just started with holographic technique. I know we were going to be developing holography algorithms, so I wanted some ground truths before starting to combine it with other methods. It's true, like the hologram quality and the training quality will be dependent on the type of shapes that you generate. And we've tested it on various types of shapes. So these are disks perhaps the one where we got the nicest result. You can make little squares. We actually try working in natural images, but we haven't done much on that end. There was some ongoing work in improving the algorithm for that. When you're trying to generate like particular shapes like images, you start going into the problem of having a relevant cost function. So the L2 norm does not provide the same level of like variability where you need it to be. And so we are currently working on developing better norms to make sure that the holograms we get are trainable. The algorithm can be trained for those holograms. But for sparse distribution, I would say like dots and disks and squares and lines, this is sufficient for now.
Great. I'll just maybe add one other comment just to the people in the workshop. You know, we talk about these things in terms of photo stimulation a lot, but one of the big applications where this could also become useful is when doing voltage imaging. So in voltage imaging, you generally want a lot of illumination only on a few specific areas to control the complexity of the imaging. And the ability to make nice, smooth kind of holograms that target specific places in space, whether 1 photon or 2 photon, is also a great application of these techs. So I think this method has that broad applicability beyond just stimulation and into imaging. And Nico was maybe going to comment on that, but I had to throw it out there.
Oh yeah. No, I actually was thinking about adding some slides on 1 photon technique, but then I remember that the core of the mnemonic conference is 2 photon. If you have 1 photon questions, we can talk. I have a paper coming out soon on the topic. Yeah, what I wanted to show on this slide is really like to keep in mind is that there is the same amount of laser power has been used to generate those 3 holograms. All we did is swap the phase on the SLM using the result from 3 different algorithms. And what you will find is that, well, you know, there is the same amount of infrared light. And what happens is that in the holograms that are not accurate, the infrared light is just scattered in the rest of the field, in the rest of the 3-dimensional environment. And it still contributes to heating up your sample. It just doesn't give you the excitation that you're looking for. So you can think about it in terms of like energetic waste of the photonic response. So, I mean, this is kind of like to give you a couple highlights on what we're trying to do next, is that we're going to combine this holographic technique with another stimulation technique that I developed when I was a postdoc called 3D shot, in which we combine the benefits of 3-dimensional holography and temporal focusing. So temporal focusing is an additional spatial compression technique that uses a diffraction grating to split short pulses into colors and constructively recombine them in a specific spatial location, so at the image of the diffraction grating. When you do temporal focusing, by stretching the pulses in time, you destroy the ability to have those pulses contribute to 2-photon excitation, but you recreate it in a very narrow Z location. So temporal focusing is very, very appreciated because it allows you to target a very wide area in 2D while being extremely narrow in the 3rd dimension, which is typically the one where having good compression is difficult to achieve. So temporal focusing is very common in multiphoton microscopy and is commonly used. What was difficult to do is combine this with 3-dimensional holographic targeting. So we came up with a solution in which we create a temporally focused object, and then we send the wave coming from this modulated object onto an SLM using a phase shaping object right here in the image plane to make 3-dimensional holography and temporal focusing compatible. And then if you compute here holograms made of points, you'll basically get 3-dimensional temporally focused object copied at every point in space. So there's a couple papers on the topic. This is 3D shot. It was originally developed with other holographic techniques, and then now we have another one which is compatible with that type of implementation, and that's kind of one of our next steps. Yeah, so these are what we could do with 3D shot. So this is our point spray function. This is the type of holograms that we're able to generate. So 50 targets at once, 200 targets at once. Visually, you can see that like we're able to get those holograms by using a super powerful laser and observing it through a slice. The downside of this image right here is that there is multiple watts of light that have been sent onto the slide to generate those holograms. So we're not trying to improve further on this type of illumination pattern, except by just creating more accurate hologram, which will allow us to get the same type of three-dimensional photostimulation, but for a fraction of the total amount of energy that is previously used in those setups. And this is really the end goal. This is the 2018 neuroscience paper by my colleague Alan, in which he used 3D shot to target ensembles of neurons. So we did ensembles of 25 cells, ensembles of 50 cells, but not much more. Why? Because at 50 cells, repeating the operation over and over, we were already reaching the line, the limits of what was acceptable in terms of brain heating. But with a better algorithm and with the next generation of opsin, so there is actually a Chrome 2 that's been recently developed out of the Adesnik lab that has even more photosensitivity. The hope is that using those improvements in the opsin and the improvements in the algorithm, we can get similar results, but with more neurons at once. And if you have more neurons at once, you can start targeting broader ensembles and start playing with the brain in a more controlled fashion. So ideally, if you want to affect behavior, larger ensembles are commonly accepted to be of greater importance. Other things that we're developing is really looking back at what the algorithm can do. You remember I said that the cost function can be customized. We are developing cost function that specifically target the goals of what our holographic techniques are designed for. So for instance, in two-photon excitation, when we optimize the difference between the hologram we want and the hologram we can create, we might as well optimize for the square of the intensity distribution, which is the two-photon response, because that is our end goal. And so when you specify in the optimization problem that you're trying to optimize for a specific two-photon response, your algorithm has the liberty to come up with holograms that are perhaps less visually interesting, but more suitable for the particular excitation that you're trying to achieve. So this is an example where if you compute those holograms using a cost function that is tailored directly for the two-photon excitation, you can get more confined and more usable distribution. So you can see here there's a lot of speckle in the image that we created. A norm that would optimize for the image intensity will try to smooth out those speckled image, and by smoothing it out would likely extend it in the three-dimensional space. I don't have the data. I wish I had taken that. But the idea is that it would look very closely to that type of distribution and perhaps not achieve the same confinement that you're looking for. But if you optimize for the two-photon response locally, or even you could optimize for the two-photon response inside the neuron, you can come up with solutions that are perhaps less visually appealing, but who cares about that? But ideally solutions that are meant to best stimulate the neurons that you're trying to stimulate. Another thing you can optimize for, and this is kind of a concept idea really, is you can optimize your cost function for spatial features. If you know where your neurons are located, instead of just putting a reward for properly targeting the neurons that you're trying to stimulate, for instance, the neuron in red, you can also add in your cost function a hefty penalty for any light that touches the other neurons that are in the space and that are photosensitive because they're labeled with an opsin, but that in the specific hologram you specifically don't want to target. So if you can include that in your optimization algorithm, you'll be able to come up with holograms that look like this. So this is kind of a representative image. You can see that light has been basically like shot in between the targets. So like your algorithm basically has an understanding of what the spatial distribution of your targets is. And because of the hefty penalty you put on the blue targets, tries really hard to not send the light along those directions. So when a photon is sent towards a target in red, the algorithm makes sure that along this line of path for your photon, the light does not end up in any of the off targets where it would increase the penalty. So this is basically what we call task-based holography, where by including features that pertain to the type of light matter interaction that we're shooting for, or the type of tissue that we're shooting into, you can come up with yet another level of improvements in the hologram quality and in the desired outcome. And with that, that's all I have for you today. Our algorithms are posted on open source platforms. The comments, the feedback, and the bugs are always, welcome and will help us improve our stuff. So Haas published a paper in Optics Express in which all the details about Deep CGH are disclosed. It is also available for questions as needed. And we continue to curate the Deep CGH code with your feedback. So if you happen to use it and run into problems, by all means, fly those problems back to us. And if you get good results, don't hesitate to add our paper in your citation list. And with that, that's all I have for you, and I'll gladly take any questions. Thank you.